Hi ladies and gentlemen. In the last videos we understood the operation of a multiplexer. That is, what is it doing? Some 2 raised to n data are coming in, and this multiplexer places these data uh, sequentially on a single data output line. So that way many sources can share the same data line or data channel. So today we see the reverse operation, that is the operation of a demultiplexer. What the demultiplexer does is there is a single data coming in, maybe it's a multiplexed data coming in, and this data are placed on 2 raised to n output lines. So one single data line is coming in, and this data are placed on 2 raised to n output data lines. So this is based on the select lines. This placement is based on the select lines. So let me start with that presentation. So this video is organized into your learning outcomes, then a circuit of a 1:4 demultiplexer with AND gates, and then the implementation of a 1:4 demultiplexer on breadboard, and then a 1:8 demultiplexer using the IC decoder or demultiplexer IC 74138. Then implementation of a 1:4 demultiplexer in Verilog, and the summary of your learning outcomes. So what you will learn in this video is that you will learn to implement a 1:4 demultiplexer in QUCS and Verilog. First I will show you the AND based circuit, and we will implement it in QUCS and Verilog. Then you will learn to implement a 1:4 demultiplexer in Verilog. Then you will learn to implement demultiplexer using the 74138 IC. 74138 is a decoder bar demultiplexer IC. We will see the pinout and wiring diagram. So the circuit diagram of 1:4 demultiplexer is shown like this. So there is a single data input line coming in. This may be a multiplexed signal coming into the receiver. So this I have to place 2 raised to n data lines. This is a 1:4 demux. So this is a 1 data line and 4 data input line and 4 data output lines. Now since there are 4 data output lines, there should be 2 control lines, log 4 to the base 2 control lines. So these are the x and y, or s1 s0, they are the control lines or select lines. So they are inverted here so that different min time, 4 min times do result. The first min time, that is x bar y bar, that goes into the first AND gate along with the D. So when xy is 0 0, what will happen is D will appear at I0. All other gates will be disabled, because this gate it is given 0 1. Okay, this y is a 1 and this is a 0. Then this is fed with next min time, that is 1 0, and this is fed with 1 1. Okay, so when the xy time it is 0 0, D will appear at I0. And when it is 0 1, D will appear at I1. When it is 1 0, D will appear at I2. And when it is 1 1, D will appear at I3. Okay, there may be an additional common pin called an chip enable signal. That depends on the type of circuit you use. This is a simple representation showing the 1 data input and 4 data outputs, and how the select lines are used to place the data on one of the selected output lines. Now you can simulate this in QUCS. If you go to this QUCS, you can simulate this in QUCS this way. This shows the my circuit diagram. Here I have added here I have used a 4 input AND gate along with an enable. This enable is kept at high, and data is given in parallel to the 4 AND gates. And here the select lines S1 and S0 they are selected, so that M0 goes into the first AND, M1 goes into the second AND, M2 goes into the third AND, and M3 or a 1 1 case, S1 S0 that goes into the fourth AND gate. So these are my output lines I0, I1, I2, I3. So here I have fed with S0 is a 1 nanosecond pulse, and S1 is a 2 nanosecond S1 is a 2 nanosecond pulse. So that and here I have given some arbitrary data, that is low for 1 nanosecond and high for 2 nanosecond. So I can run this simulation, and you can see the waveforms coming in. This is S1 and S0. These are the select lines. These give the pattern 0 0 0 1 1 0 and 1 1. Now this D initially it is up to 4 picosecond. This is a low. So what happens is this is placed at I0. When it is 0 0, I0 is a 0. When it is 0 1, I1 is a 1 0. Sorry. When it is 1 1, I3, that is a low because data is a low. And when it comes here, you can see that if I look at this I0 here, what happens is this is a 0 0 coming in again. Okay, now the data is 1, so I0 becomes a high. Okay, now at this time this becomes a 0 1. Now I1 becomes a high. You can see that I1 becomes a high because the data is high. And at this point it is a 1 0 1 0 case. Here I2 becomes a high. You can see that I2 becomes a high. And at 1 1 at this point it is 1 1, so this I3 becomes a high because data is high from 4 picosecond to 8 picosecond. So this is how a multiplexer places a data on different output lines. So let me go back to my presentation. So this is how I can use the AND gate IC 7411. It's a 3 input AND gate IC. So 4 input AND gate IC. So here you can use these ICs to wire up my circuit. Here you can see that this data line is a common one. This line is a common one. Then different min times are selected. Like I have these times S1 S0. These are AB select lines. Okay, these are a B complement and this is A complement. So different min times are connected to different gates along with my common data, which I keep it at a high. So this is my D input. This is my D input. This is common to all the gates, all the 4 gates. So this D is placed on the output lines, which are the output lines, output of these AND gates. So here I have, these are my AND gates. So here I have placed 4 LEDs that are normally on. That is connected to the supply through a 220 ohm resistor, and you can put D equal to 1, and you can apply different inputs to AB like 0 0 to 1 1 1 with the help of toggle switches, and you can observe this output. Keep D at high and observe this coming at coming at I0, I1, I2, I3, etc. So that way you can verify the circuit with the help of breadboard and MSI chips, 7411 and 7404 chips. Okay. Now along with that you can familiarize a chip called 74138. It's a commonly used 8-line demultiplexer or decoder we will see in the next classes. You can look at this wiring diagram. This is a 74138 IC. It has a 3 select lines, A0, A1, A2, because it's a 1 to 8 demultiplexer bar decoder. So I should have 3 select lines, A0, A1, A2, and here you have 2 enable pins are there. So the 3 enable pins are there, so you place them at logic 0, and as two enable pins are there, they are kept at logic 0. This is an active low enable. Data is given to the 6th pin. This is the input point, 6th pin, and these are my output. O0, O1, O2, O3, O8, O7 are my output. These are active low. These are active low output. So instead of D complement will come at the output. So 8th pin is grounded and supply is connected to VCC. Now what I do is I connect 8 LEDs in the normally on configuration, and I apply different patterns here: A0, A1, A2, A1, A0, 0, 0, 0 to 1, 1, 1. I give pattern 3-bit patterns with the help of toggle switches, and then I observe this D appearing at O0, O1, O2, O3, O4 to O7. This you can do in the lab. You can go to the lab, ask for a 74138, wire up this, connect 8th pin to ground and 16th pin to VCC, then wire up this circuit diagram and verify this configuration. Now I can have a 1:4 demultiplexer in Verilog also. What I need is I have to use that 4 input AND gate I made previously. So what I do is I grave include 4-bit AND dot V. So I use this 4-bit AND and to generate this 1:4 demultiplexer. What I will show you the code. So what I do here is I go to this location, this is a 1 to 4 demux, the 1 to 4 demux. So here I include the earlier made 4 input AND gate because it is very easy with a 4 input AND gate. So I start a module with some name 1 to 4 demux. Output wires are, I have 4 output lines, I0, I1, I2, I3. Input wires are D is there, then A0, A1, the other select lines, and 1 enable pin. So there are some locally internal nets because I have to complement this A0 and S1, so they are A0 bar, S1 bar. Now this NOT gate is, 2 NOT gates are used for complementing this S0 and S1. So this S0 bar is S0 complement, and S1 bar is not a version of S1. Then there are 4 input AND gates. So here I first AND gate has an output of I0. What are the going into this input? The first min time, that is S0 bar, S1 bar, then D and enable. Now next one it's a 0 1. Next one, it is I1 is the output, S0 S1 bar, because it is a 0 1 configuration. And then D and enable of to N5 output is I2, and N6 output is I3, and inputs are A0 S1. That is 1 1 case. D and enable goes into this. So then N module. Now I can write a test bench. I can write a test bench for this. I can include this 1 to 4 demux, grave include 1 to 4 demux. Then I create a module test bench. These inputs are given as registers D, S0, S1, EN enable, and outputs are wires I0, I1, I2, I3. Then I make an instance of the 1 to 4 demux this way, I0, I1, I2, I3, D, S0, S1, EN. Then I give these values, and then I apply some patterns for S1, S0, D and enable. Okay, I have to keep this enable at a high for proper operation. Now I can run this, I can verify this code by running with iVerilog. I compile the device. Now the device and test is compiled without any problem. Now I run the test bench. I specify some output file a.out. Okay, then I run the a.out .a.out. So you can see that initially at 0 nanosecond everything is ambiguous. At 10 nanosecond what happens is S0, S1, 0, 0, enable is high. So what happens is D will be I0. What is D? D is a 1, so I0 is a 1. And at 15 nanoseconds, so what happens is S1 is 0 and this is a 0, 1 case. Okay, so I1 should be coming out. I1 is a 0, so D is a 0. And at 20 nanosecond, you can see that S1 is 1 and S0. That is I2 will come out. I2 is a 1, so D is a 1. Again at for 1 1 case, you can see that I3 equal to 0. I3 comes out now, that D equal to 0. Now when this enable equal to 0, whatever that previous output is there, it remains at that. With enable equal to 0, the system does not work. Okay, so this is how I verify the operation of a 1 to 4 demultiplexer in Verilog. Now let me go back to my presentation. So this is a summary of what you learned. You learned to implement a 1 to 4 demux in QUCS and Verilog. Then you understood the wiring diagram of a 1 to 4 demultiplexer in with gates, and you learned to implement a demultiplexer using 74138 IC. And that's the end of this presentation. I thank you all.